What I thought we'd do today is go back a couple of slides and think about this activating, deactivating thing so that we are happy with it. This is confusing, and especially when you've got a couple of days to learn it before a test, it can be a bit overwhelming. I will tell you where we'll cut off. Some of this will be on there, no doubt, we've covered it, but I won't be trying to get to the end of the chapter. We'll save that for when we come back, okay? So in terms of today, I've got to be home by 3. I'll be gone pretty quickly after recitation today. But tomorrow I'm pretty open. I have one class in the afternoon from 3 till 4, so if you want to catch me before, then do so for Friday's test. This is an important test. It's a difficult test. I would describe it as a busy test. Okay? And if we can get some extra time on Friday, we will, a couple of minutes. But you will be pushed on Friday, right? So be ready and be on top of stuff, and we'll see how we do. Now, I'm talking about nitration. I'm talking about here toluene. This is an example of an activated substituent in which we are pushing electron density into the cycle. The methyl group here is donating electron density. And if we do that, we find that the benzene ring now is more nucleophilic than it would be if it were benzene itself. And that means it reacts faster, and that's exactly what activation means. This system is going to react faster than benzene. We already saw this a little bit when we talked about the idea of over-alkylation, the fact that the product is more reactive than where we started, and we get competition. But if we isolate this stuff and then we go and react it again with, let's say, nitric acid and sulfuric acid, it turns out this next step will be faster than if it were using benzene. That's the whole point of activation. And the regiochemical outcome then is separate. Yes, the reaction goes faster, but it's all about where things go. And where things go is really crucial here. When we drew this out for toluene, we saw that the actual outcomes down at the bottom, we were favoring the orthoisomer and the para isomer, not the meta isomer. And I'll say this now, hopefully you've had a chance to read this. It's all about the potential carbocations that you can make. And if you have carbocations with some tertiary character, they will beat out any carbocations that don't have tertiary character. And when I get to the withdrawing groups, you'll see the flip. You'll see the opposite side happen, the opposite way around. You want to avoid the carbocations next to the electron withdrawing group. So here we have this fairly simple system. You'll see now that the 5 sets of reagents that you learned, the idea of nitration, bromination, the idea of Friedel-Crafts alkylation and acylation and stuff like that, all apply now for the second substitution. It's the same type of idea. Mechanisms are the same. You're generating the same electrophiles. So if we generate NO2 plus in this system, we find that the major compound here is the orthoisomer. They're very much the minor compound is the meta. We might describe that as a trace of material, as a trace amount of material. And we get a significant amount of the para situation. Now, the whole point here is the methyl group isn't that big. It's going to help substitution at the ortho and para positions, but it's not going to block the ortho positions. At the end of today, you'll see that big groups in that position will block out the ortho groups, and sometimes you get more of the para substitution product. But right now, we're talking about an activating group, which is an ortho-para director. And if you've had a go at this, it should become fairly straightforward. If you understand resonance, which most of you, you all passed the first class, you should be comfortable with resonance. If you can draw these structures without having to memorize them, it saves you a lot of time and a lot of pain. And you can see now that the 3 instances here are showing attack at the ortho position, and that simply is the arrow coming from that pi bond attacking NO2+. And that gives you a carbocation which can be described by those 3 resonance structures. They all have 3 resonance structures, but the one at the top has a resonance structure with some tertiary character, right? That situation there has some of the charge next to the methyl group, hyperconjugation comes into play, and that is a better picture. So overall, that carbocation, if you draw the resonance hybrid, is good, right? It's better because it takes advantage of the fact that the methyl group is helping out. At the bottom, similarly, if you push the arrow towards the nitro group from the para position, then you can put some charge here, and you can put some charge there in the same way. You can put some charge next to the tertiary carbon, and that certainly helps. In the middle, no. If you look at where the charges are in the middle, then it doesn't go next to the methyl group. Now, if you're getting, if you're trying to bluff your way through here and guessing on resonance structures, this is where it all falls down, right? It all gets really ugly. If you understand resonance, this is pretty straightforward. We can talk now about the fact that this is not so good. These 2 are fine, and that's why we get the reaction going in that direction. Yes? If you can do these diagrams, you can do this directing effect. So that's the idea for the toluene with the methyl group. There are the reaction profiles showing you the first step, the rate determining step in each process right there. On the left, we've got the ortho attack. On the right, you've got the para. The ortho is a little bit higher because there is some steric environment around that methyl group. There is a little bit of a problem, but not so overwhelming right here. The middle is the worst of the lot. The middle is where you couldn't put any charge next to the methyl group, and therefore that's the slowest reaction. Now, in terms of other types of groups, if you've been reading ahead, and I've been getting questions this week on this type of thing, so people are reading ahead, we have extra help. We can now think about lone pairs directly outside that cycle. If a methyl group is good, then a lone pair should be better, because a lone pair should be able to be localized into the cycle, and it should be able to stabilize intermediates. You remember that hyperconjugation is good, but resonance is better. And if you can get both, you're in great shape. So even though the dipole for this molecule seems to be going towards O, that's through the sigma bonds. That's through the single bonds. When we're now thinking about using this molecule in electrophilic aromatic substitution, we need to worry about those pi electrons, because those pi electrons, or those lone pairs, can be pushed into the pi system, and they enhance the nucleophilicity. They make this reaction faster because of these pictures. And you could argue now that the carbons at the ortho positions are delta negative, making them quite nucleophilic, and the carbon at the para position is delta negative, making it nucleophilic, even before the reaction happens. So that's why it's going to react faster. Now, when we actually do the chemistry with this molecule, anisole, and compounds like it, which are moderate to strong activators, we now see that we don't need a catalyst. So the catalyst now is unnecessary because the starter material is so reactive. The methoxy group enhances the reactivity of the benzene and makes this way more reactive. So in this example, no, we haven't forgotten the catalyst, we just don't need it. And I had a question yesterday, am I expected to know where all these bromines go if I get over-bromination? Yes, you should know where they go, but I would tell you, I'll give you a hint as to how many times it happens. Okay, you're not experts at this yet. When we come back after the break, maybe, but you'll be guided to what's going to happen. So now we've got a situation in which 3 brominations happen. This should tell you a lot. You don't need a catalyst, so the reaction's fast. You don't need to speed it up. You might need an excess of bromine. That might be a clue to be able to see that that's going further. And it's going to the ortho and the para positions exclusively. And at the bottom you see again, in this example, we have ortho and para a major, because this is a ortho-para director. And again, it's going to be about stabilizing the carbocation in those 2 instances where we add at the ortho and we add at the para position. In this example, we can see there's a switch now. This actually, the ortho position is less favored than the para position, and that's simply to do with steric environment. You've got this methoxy groups flying around. It's going to block out some of the electrophile coming in. So the para now is favored. But it's the same argument we just did for toluene. The diagrams right there, again, please try to learn how to do these things ground up. Don't memorize them. When we come back after the break and finish this chapter and head into the last material, the last few chapters, memorizing is painful. Understanding it makes it a lot more enjoyable, a lot more reasonable. So what I have here is, again, what's happening at the ortho position when we attack there. We can see now a positive charge building up next to the oxygen. This now is good because we can use the lone pair from the O to help stabilize it. And in fact, we get a 4th resonance structure. And the more you can spread out the charge, the better. The more resonance structures you have here, the better. So having 4 is better than 3. Down at the bottom, if you were to put the NO2 group or whatever electrophile, E+, whatever you've learned as the electrophile, SO3, acyl group, stuff like that, if you put them at the para position, this is okay, this is great, right? This is now starting to look like a situation where we can use the lone pair and we can get that 4th resonance structure again, and so that benefits the system. And so the ortho and para are favored. The meta, you cannot put the charge here, right? There is no charge going next to that O, therefore the O can't help. So for the activating groups, it's fairly clear. Put the charge next to the substituent helps. If you don't put it there, the substituent can't help. In terms of reaction profiles, again, you're familiar with these things, you're familiar with transition states, you should be able to draw these things, again, from scratch without memorizing everything. And we can see here, ortho, a little bit higher than the para situation, and that's down to the steric effect. They're both helped by the external substituent, but the one on the right is favored because the para position is not crowded at all. It's too far away from the methoxy group. And the meta situation is the worst of the lot because there's no help from that substituent. Yes? Big exam Friday. Be here early. Be on your toes. Okay, we get started as soon as we possibly can. Now the opposite. This adds up, I think. If you want to put a positive charge next to a donating group, you don't want to put a positive charge next to a withdrawing group. Okay? Donating groups help stabilize positive charges. Withdrawing groups destabilize positive charges. So it's completely the opposite. That's all you need to worry about. Nitro is one of the worst. Nitro is a very powerful electron withdrawing group. It is deactivating. That means the benzene ring reacts slower, or the phenyl ring reacts slower than if it were benzene, because it's less nucleophilic. In fact, if you were to draw a resonance hybrid for this, thinking about these resonance structures, you wouldn't be putting delta negative on here anymore. You'd be putting delta positive. And since you think about the chemistry here, what's being asked to happen is that we're asking the benzene ring to go after something positive, something electrophilic. Not quite so good, right? It's certainly not nucleophilic or as nucleophilic as it was previously. So know what your electron withdrawing groups are. We've done all the functional groups. You should recognize that anything with a positive charge or a delta positive charge, this is something worth writing down, anything with a positive charge or a delta positive charge directly outside that cycle is going to slow the reaction down, and it's going to be a meta director. That's all you have to worry about. After that, it's the same mechanism again and again. So now the electron withdrawing groups have the opposite effect. They slow things down for the most part, and they are going to be meta directors. Now, this is a bit clumsy the way we described it on Monday, but this is the best you can do. This is going to be the least worst, the least bad, right? This situation for meta is not as bad as the ortho-para situations. So what we've got down here is the experiment showing the reaction between nitrobenzene and nitric acid sulfuric acid. The 100 degrees C is an indication of the fact that this is a pretty slow reaction, and you have to speed it up. Why is that? You should be able to explain it. It's because the NO2 group is electron withdrawing. It's slowing down the next step. We do see now a switch. I have a little bit of the ortho coming out now. We get a lot of the meta situation, and we get very little of the para situation. Now it's this, we switch, it's the opposite. If we think about how this is happening, again, the best way to do this and to describe it, if you're asked this type of question, is to draw some resonance structures and to show how this is set up. So at the top, we now have the ortho situation again. It's the same mechanism as we did in recitation, we did in class on Monday. It's the same mechanism again and again. You're adding the electrophile. This is simply E+. Go add the electrophile to the ortho position, see what happens. At the ortho position, we start building up charge right here. Is that good or bad? Bad, terrible. Now there's a universal symbol for that. We'll use this. Okay, that isn't good. We don't like that. That's allowed on exams because it's very quick and speedy. We're okay with this. We're okay with this, but we don't like the first one. So that's terrible. Yuck. Okay. At the bottom, this is fine as we're building up charge on the metacarbon. This guy here, no, not happy with that at all. That situation is terrible. So again, these are not separate carbocations. That's something subtle that has to come out, especially if you're looking for the high grades in the class. You've got to recognize that these are not separate carbocations. It's one carbocation described by these different pictures. And if we had to draw an overall picture, we'd be putting delta plus right here, not full positive, and that delta plus is still bad next to that nitro group. You don't want it there. So this again, bad. And so by default, the least bad or the least worst, or the one that isn't as bad as the others, however you want to say this, is this. And this is, I'm not even going to do that because it really isn't. I'm going to do this as okay. All right, this is okay. It happens to be the lowest energy pathway. That's where the molecules will go, and that's why you get the major product being the meta situation. So you don't have this problem in the middle where you've got the charge next to the nitro group, and that's the best you can do. So take home from there. Nitro groups and similar electron withdrawing groups slow down the next reaction. Sometimes you need more pushing conditions, more harsh conditions to make the reaction go because it's slower. But then when we come to think about the carbocation intermediates, you're looking to avoid the charge next to the substituent. And as we progress through the last slides today, you'll see things like ketones, things like carboxylic acids, things like esters. With that carbonyl right there, they are electron withdrawing, they are meta for the same situation here. Anybody? Michael. Yes, you can. If you want to abbreviate things, you can use this. The question is this. If you're not doing electrophilic aromatic substitution and you're trying to draw a benzene ring quickly, I'm fine with this. That's fine. That's a nice quick abbreviation, yes? But when you're drawing electrophilic aromatic substitution, you need to use a Kekulé structure to show where the electrons come from. That's fine. Dominic. Okay, this you do not want this structure. Do you see from the back where the positive charge now is next to this nitrogen? That nitrogen is positive. You do not want two positives next to each other. And that's the situation with the ortho at the top and the para at the bottom. It doesn't show up at the meta, so that's the pathway the molecules go. Graphs showing this. These are all higher reaction barriers than they were for benzene. That's why it's slower. Why is it slower? It's electron withdrawing. It makes the benzene ring less nucleophilic. But again, ortho and para destabilize now. Meta isn't so bad. That's the best you can do. So we left off with this. And I think it was worth summarizing that so we can get into today and finish this off in terms of time for the test, and then come back and finish off the chapter on the first day after the break, and then we'll give you exams back that day, and then we're into the second half of the term. And then it just flies along. So what have we said so far? Activators push electrons in. We could use maybe this little symbol that we've seen before. Activators push electrons in. Deactivators pull electrons out. And we can argue that that activator prefers to send groups to the ortho and the para positions. So simply here, this is the ortho position on the one side, this is the ortho position on the other side, and that's the para position. Every time, they will be your major products. So for activators, you're only going to get ortho and para, or you're going to get them as the major products. You get a very small amount of the meta. In this example now, the deactivators that you have seen so far, nitro, we'll see ketones, nitrile, C triple bond N, things that you've seen a little bit of before. Those tend to be meta-directors. But there is one issue. There is one problem. One group of molecules does not fit into this nice little clean-cut sort of paradigm. And they are the halogens. The halogens are a little bit different. Now, first off, I'm going to draw this and see if we can start by doing this and then compare the differences. When you think about chlorine and you think about the halogens, often they are comparable to oxygen or nitrogen, okay? Because this had a pair of electrons that could be donated in, and this guy has electrons that can be donated in. And what we'll say now is that the halogens don't fit this same idea. What we drew just now and on Monday was the idea that these electrons can be pushed in. That enhances the nucleophilicity. It also stabilizes carbocations when you go ortho-para. The problem with this is that it's actually deactivating. Over here is activating. The halogens are deactivating. All that means is that they react slower than benzene. The rate of reaction is slower than benzene. That's because we have electron withdrawing ability of the chlorine pulling electrons away from the ring. Well, we countered that by pushing electrons in. We said that even though the oxygen is electron withdrawing through the single bond system, it's donating through the pi system. This isn't happening with the halogens. The halogens can be equally as electronegative as O or N, but the problem is they're not so good at pushing electron density into the cycle as is. What's the difference between Cl and O? What's always been the difference in terms of some of their chemistry? Size. Yes, size. So chlorine's significantly bigger than oxygen, and it's significantly bigger than the carbon next to it. Whenever you see that, and you'll see it more after the break, you have diminished overlap. If you have a disparity in sizes of the atoms, they don't overlap as well. So it turns out this type of donation into the cycle isn't going to happen at that stage because they're not the same, they're not big enough. The chlorine is too big. It's just not going to overlap very well with the carbon next to it. So the deactivation here is about the fact that the sigma bond kind of wins. Or pulling electron density away from the benzene ring through the single bond wins. Well, what we'll find now is that the problem is they are deactivating, but they're also ortho-para directors. Let me summarize that. Everything we did so far, activation was ortho-para, deactivation was meta. Now we have a deactivating group that's ortho-para. So this needs whatever you put there to go, what the hell just happened? Asterisk, whatever it takes. This is it. This is the odd one out, or these are the odd ones out. So the problem is we don't have a lot of help from the chlorine because the chlorine is too big to push electron density in. But when we get to the carbocation stage, the chlorine has to help, right? The chlorine will have no choice. So first off, this is deactivating. But they're also ortho-para directors, simply because now they do have lone pairs. And if your carbocation, which is missing electrons, is desperate for electrons, the chlorine can help. It doesn't help as well as the oxygen because the oxygen is the same size, but it does help at the carbocation stage. So let's think about this. This argument here about deactivation is going up the transition state towards the transition state for the rate determining step. This is at the carbocation stage. So you're at a different place on the graph. Now we can get some help. All we've done again is set up the ortho-meta-para substitution possibilities for the system. And we can see here at the ortho attack, we can put some charge next to that chlorine. Okay? So now we can think about it switching. When we think about activation, we think about the atom outside pushing electron density in. When we form a carbocation, you can think about the carbocation pulling electron density in. The carbocation needs some help, so it's pulling electrons away from the chlorine to help out. And so we get the possibility now of some delocalization onto that carbon, which is represented by that structure there. You can get that fourth resonance structure. It may not be as good as for oxygen, but it's better than nothing. So the chlorine can help out. So you get this fourth resonance structure. That's good. At the bottom for the para situation, yes, that's fine. That's fine. That's fine. But having some of this positive charge next to the chlorine enables chlorine now to help. The carbocation is kind of borrowing electron density to help stabilize. So in both the ortho and the para situations, you get this extra resonance structure. And that extra resonance structure benefits the system. You don't get that in the meta situation. So what you really need to worry about here is more about the deactivating effect in the ortho-para, because the ortho-para fits. I've said before, if you have a lone pair directly outside the cycle, it will be an ortho-para director. These are ortho-para directors. It fits that same idea. The only difference is how fast they react. Okay? So don't get lost in that. Don't get overly confused by that. Yes, they react slower, but they react in the same way as all the other atoms that had a lone pair attached. There's nothing different there. If you're okay with that, it's easy enough. Hello, Catherine. What's up? It depends what's attached to it. There's a list coming up in a minute. All right, but they tend to be activating with that lone pair helping out. So far, so good. You want to write something down? Anything with a lone pair outside the cycle is an ortho-para director. There are some very simple generalities you can make here, and they work. Because that lone pair can stabilize carbocations. That's your major concern. You're not that concerned about how fast things go. You're concerned about where things happen. Michael Bartholomew de Coley. You can do, yes, I think you can do electrophilic aromatics on fluorobenzenes. You can do the same reactions on fluorobenzenes, right? And I think there's actually maybe a slide coming up to explain some of that in a second. Right? But that then gets into the fact that fluorine's the same size as oxygen, roughly, but it's still a bit deactivating because it's so electronegative. So you've got this balance between how electronegative is the thing, how electron withdrawing is it, and how big is it, which are things we've dealt with before, just putting it all together, just mixing it all up. Okay, so with that in mind, let's think of some summary, some sort of guide as to what to do here. And again, there's some of this on there on Friday. It's not much of it on Friday, right? We've covered an awful lot of other stuff. We've got all the spectroscopy stuff that you've done. We've got the double bonds, the aromatics, all that stuff, and we've done some benzene chemistry. So you might see one or two questions based on this type of idea, including electrophilic aromatic substitution. The third test, yes, there'll be a lot of it. Okay, we'll have finished everything by then, and you'll be able to decide, is it nucleophilic, is it electrophilic, is it orthopara, is it faster, is it slower? By then, you will be experts. That's about a month off. So Friday, just keep on top of this stuff. Now, okay, here we go. We're saying now that these are all activators. These are activators. These are capable of pushing that lone pair in. So if you can recognize the lone pair directly outside that cycle, the reaction should go faster, unless it's the halogens. Pierce. The more overlap you get, the better. The more bonding you get, the better. It stabilizes the system. Yeah? Think about the pi bond between a 1,3-butadiene. Anytime you overlap anything, it stabilizes the system. So here I've got strong activators. If you're not given the lone pairs, you should know by now to put them in. And you can see now that we can push electron density into the cycle from each of these species. Okay? And you can do that with nitrogen. And we can draw resonance structures, in fact, where the carbons at the ortho and the para positions become delta negative. That makes them more nucleophilic, that makes them faster. That's activation. So lone pairs, other than the halogens, are going to activate. Moderate activators, okay, we've got esters, where the O is directly attached to the cycle. We've got amides, where the N is directly attached to the cycle. And also we've got ethers at the end. Now I've got a couple of questions to ask here. These are moderate activators. They're not strong, but they still have the same atoms. But over here we had N attached. Here we have N attached. The problem here is that the lone pair can be pulled in two directions. If we don't have this carbonyl here, the N can push electrons in that direction, no problem at all. And that was this picture here. If we put the carbonyl next to it, is that electron donating or electron withdrawing? Electron withdrawing. So now we have this problem where we're getting competition and the electrons being pulled in that direction also, which is shown by this type of picture at the bottom. So you put the ester or the amide on where the N or the O is directly attached to the benzene ring, they're still activators, but not very strong. They will still send things ortho-para because that lone pair will help out. But there is a bit of competition now with what else is attached. That's one thing. Now, why might you think this is a moderate activator whereas its nitrogen analog was a fairly strong activator. Any ideas? The N is a fairly strong activator. The O analog, which is the ether, is a moderate activator. Any arguments? Samuel P. ringtone. Not by much, no, not going to make a difference. Size will not make a difference here. Any ideas? You've got a list of things to go through. I mean, that's all you have to do. It's not steric. It's usually something very simple. Electronegativity, absolutely. Which is more electronegative, O or N? O. Which will hold on to its electrons tighter, O or N? O. So this oxygen can push electrons in, but not as well as the N. Okay? The N is more nucleophilic, it's more basic because it's less electronegative, and so this is going to push electrons in better than oxygen. Little subtle things, you can read it in the book, and shows up in reality in terms of how strong the directing effects are. But again, you know, we've been saying this from the beginning. Why are 60 people missing from the first day of class last semester? They couldn't keep up with the basics, because the basics now are being applied. We've done all the difficult stuff. We've done all the basics. We're just putting it into practice. Okay, so I have some moderate activators there. I have some weak activators here. Why are these weak activators? What do they lack that would make them a stronger activator? A lone pair. That's it. Lone pairs. No lone pair, you can't push a lone pair in. But they are activators because they all do push electron density in through the single bonds. Makes sense. And so far, these are all ortho-para directors. Now we go in the opposite direction. Deactivators. Mikey, this will answer your question. These on the top are all deactivators. So that's saying basically, this isn't so good. Okay, why should that be obvious? Why is that a fairly intuitive thing now at this stage of your chemical lives? Fluorine pushing electrons towards something. It's too electronegative. It's the highest electronegativity. It's greedy. It wants its electron density. It isn't going to play ball and help out. Right? So it doesn't do that. Even though it's the same size as the carbon next to it, or roughly, it doesn't do it so well. Chlorine's bigger. Bromine's even bigger. Iodine is large. Okay? So we just don't get that overlap as well. So the activation idea here doesn't work. Other groups, down at the bottom, we've learned these in the past. There's nothing here you haven't seen. We've already made this semester, the SO3 type group, and we've seen this in the past. All of these things have something in common that make them deactivators. And all you have to recognize now is that the carbonyl carbon right there, what symbol should I put on there? Delta plus or delta minus? Delta plus. If you understand delta plus there, that's most of the second half of the semester. That delta plus is key to a lot of that other stuff to come. So delta plus here, delta plus here, delta plus here, delta plus there. Guess what? Delta plus there, delta plus there, delta plus there. If you recognize a lone pair, activating. You recognize delta plus or full positive, like you see with an N and a nitro group, deactivating. Catherine. That's right. So I'll finish that off by summarizing as follows. The only little hitch you'll have here, this is on the same slide as all these other species, but these are ortho-para directors. These are all meta-directors. That's the key. That's the confusion. That's what you spend 5 minutes thinking about, and it's straightforward. It's the only problem there. It's good stuff, this. If you like this stuff, come back for the second half. It gets better. Piled higher and deeper. So with that in mind, think about some of the strange substituents that you maybe haven't seen or are not commonplace that you don't see all the time. Many of these other things you've seen in lab, you've seen in restation, and you're familiar with them and you're comfortable with them. This sort of stuff maybe, certainly the top two types of substituents, maybe you're not so familiar with. But if you were to think about nitro, I think by now we ought to be able to draw out what a nitro group is. NO2+, right? That's important. And that opens up the fact that that middle N is very electron poor. It's very electron deficient. That's why it's deactivating, because it's pulling electrons towards itself, slowing down the benzene ring in terms of its nucleophilicity. This thing, when we put 3 or 4 things on N and make it positive, is that electron donating or withdrawing? Withdrawing. What happened to the lone pair? It made a bond. Good, it made a bond. It's no longer available. Now, one of the big problems on restation quizzes this week and the exam this week is the inability to count up to 4. And people just cannot stop at 4 and they want to go to 5. How many bonds has carbon always had? Have you ever seen it with 5? It shouldn't be 5, right? It should not be 5. How many can nitrogen manage maximum? 4. Same way, 4. Got 8 electrons, fill the octet rule, it's 4 bonds. Not 5 or 6 or 7. At this stage of the game, that's an F. Now, this thing over here is said to be a strong deactivator. Notice that the carbon here is actually in the way of the halogens. These are fluorines or bromines or chlorines. But this is a strong deactivator. Because even if you send the atoms a little bit further away, those things are electron greedy. Imagine putting a CF3 group here. That is powerfully electron withdrawing. It's an unusual one that you haven't seen much of, but it fits into the idea of deactivation because it's so electron withdrawing. And what do you think its effect would be in terms of directing? Would it be ortho-para or meta? It would be meta, absolutely. So these things, keep an eye out for those. Often, as we head into the second half of the semester, and certainly on the final, I'll throw something on you haven't seen. A group that you haven't seen before, but if you understand, from your early days of chemistry what bonding is all about, you should be able to work out, it's delta plus, or it's got a lone pair, and go from there. That's what I expect in the near future. Jessica 4. If C is a CH3 group, it's an activator. It's the opposite. Yeah? So if you put halogens on there, you start to pull electron density away from the cycle, and you deactivate it. Right? Now, I'll say this. Confusing? Yes. Logical? Yes. And it really is about how much time you put in and how much you get help and you understand things. Because it becomes very obvious on this next exam, the level of understanding. Those who get it really get it. I fully expect my high on the next exam to be 100. And I fully expect my low to be around 10. That's the nature of the beast at this school. Okay? But you all made it through the first semester, and this is stuff from the first semester. So don't be the 10. So here we have a table. I'm not a big fan of this table. It's just, it's a lot of information, but it's just summarizing what we just did. It's looking at the different groups and thinking about the ideas now in terms of generalities. Anything with a lone pair that can push in, sure, activating. Anything with a lone pair that's competing with another electron withdrawing group, not so good, moderate activators. Anything that doesn't have a lone pair are still going to activate, as we saw with toluene and the over-alkylation experiments and the Friedel-Crafts reactions, but not as well. And then we get the weird ones, right? Halogens are just different, because we're now looking at the fact that these are either larger or too electronegative to communicate with the carbon next door to activate the system, but when you get to the carbocation stage, they will help. Down at the bottom, you've seen all these. When we did spectroscopy, you've seen them all again. So you should be okay. The idea of electron withdrawing groups next to the benzene ring slows things down, and all these below this line are all meta-directors. It says so right there. But we need to understand why. And that's the killer in this class, is the why. But guess what? What comes next is all about why. Biochem, why. Everybody all right? Alessandra Volpe. Anybody back? Cody, my man, how are you? Good, man. Just keep quiet. All right. So what we'll do next is put the next substituent on. And this, I think, is logical and will make some sense. And I might do this right now, okay? That's where I draw my line for the exam. Everybody writes that down. Like it makes a difference. Write it down, because I keep getting people asking me about stuff we're not covering, because they didn't write it down. So this is the next step. This is taking a bit of time now, because I have the time, we don't have much time in the class, to talk about what comes next and to build on this and to talk about logic and the idea of synthesis. Because a huge part of what happens in the next half semester is synthesis, using this stuff to build things. And it all is based upon knowing the ortho-para directives and the meta, knowing where things will go, and knowing some of the limitations of these systems. So what we've got here is a molecule that has two substituents. If you go back to the first slide in this chapter in the aromatic stuff, where we talked about the types of compounds here, the useful medicines, very few of them had one group attached. Some of them had two. Lots of them had 3 or 4. And if you want to build that and synthesize it efficiently, you need to know how this works. So we'll find now that this system could be argued to be activating, yes? The one end is activating. The other end is strongly deactivating. So the reactivity of this thing is somewhere in between the two. You might argue this will be, is a methyl group strongly activating or strongly deactivating? Or is it neither? Is it strongly activating or weakly activating is the better question. Weakly activating. Is the nitro group strongly deactivating or weakly deactivating? Strongly. So which one do you think has more influence? The nitro group, right? So if you had to put your, you had to bet your mortgage on this. You have a mortgage, Pierce? I do. You had to bet the mortgage on it. Would you say this molecule would react faster than benzene or slower? Slower. Yeah? Argument's fairly straightforward. But it does work. We need to catalyze this one with bromine, for example, and we need to worry about where things go. And in this example, it's fairly clear. It's fairly straightforward. What is the directing effect of this species at the top? Orthopara. What's the problem with the para position? It's occupied. Yes? You can't put anything else here. Some of you will try, but you're not supposed to put anything there because it's already blocked. It's already taken care of. So that's okay. This will be ortho directing. And what is the directing effect of the nitro group? Meta. The meta position is open. But look at this. Coincidentally, the meta position for the nitro is also the ortho position for the methyl group. So you get a pretty clean reaction where both of them guide to the same place. So you can expect that to be useful. That's a high-yielding reaction. Not always the case, but in this case, yes. So lots of stuff here, summarizing all, putting it all together. What about down here? We have an OH group at one end, and we have a methyl group at the other end. Which do you think is stronger at what it does? The OH, right? The OH is a more powerful directing group. It's a more powerful activator, and so you can expect those lone pairs to be pushed in. And obviously, this and this will become activated because I can draw resonance structures in which they're delta negative. So the ortho position here, it's the stronger activating group that's winning, and it's the one that stabilizes the carbocation better that's winning. So we don't go here. This is ortho to this group. We go here, ortho to this group, because this is better at what it does. It's guiding the material into that place. Partly it's more nucleophilic there, and also the carbocation is stabilized better, and the para position is already taken up. Trish? You might get a little bit of the other one where the nitro group is down here. Okay, I don't know the actual, the other one isn't shown in the actual experiment here. It might be a small amount of trace, something like that. But that's something you have to run the experiment to find out. And to avoid confusion like that on questions, I'll just ask for the major product. Okay. So, on top of that, you can get, you can get help. You can get one group helping another to direct the next group into a certain place. And you can also get some issues of steric environment and things getting blocked out. So what do we know about this guy here? What's this? Large. It's NMR spectrum. It's pattern, doublet and septet for Friday. And you know that it's large. Is it activating or deactivating? Activating, right? It's an alkyl group. And if it's activating, then they are exclusively ortho-para-directors. But in this example, the major-minor is switched. The major is the para, the minor is the ortho. And that comes down to the fact that the position at the ortho is blocked. Put a T-butyl group on there, it's even worse. Do you know numbers? Can you tell me 65%, 35%? No. But you can tell me major and minor, knowing the basics. So this one now will be major, this one will be minor. And I'm going to say this now and say it again when we get back. If you're doing a synthesis, thinking about the third exam later, and you get both of them, you can separate them. So even if you know you get isomers, you know you can separate them. You can do TLC or chromatography. You can distill. You know you can separate them. So in a synthesis, that might be 1, 2, 3, 34 steps coming up after the break. You know you can separate the stuff you don't want out and carry on with the stuff you do want. That will be key. You'll see that in exam questions in the future. So we get this stuff, and that's obvious now because of the fact that the ortho position was blocked out. Now at the bottom, we have a competition. We have two activating groups, and the activating properties of these things will be quite similar. They're not that different. Isopropyl group versus a methyl group. And you can see now that the major is this. Why? Steric environment. The ortho position next to the isopropyl group are certainly more crowded than the ortho positions next to the methyl group, and so the methyl group will win. And it will go ortho to the methyl, and it will avoid, if it can, the isopropyl group. That's fairly obvious. And of course, you can envisage questions in which you're given an equation. You haven't seen the stuff before. Tell me what happened. Explain to me what happened. And this is all first semester gear. This is all first semester stuff. Steric environment, size, resonance, all that stuff. It's all the same stuff. Okay. We will also use a blocking group, a protecting group. And we'll use sulfonic acid to do this. Again, the idea being, what if you absolutely desperately need your bromine to go there? If you react this material with FeBr3 and Br2, where will the bromine go? The para position. It will go here because the ortho position is blocked. So how do you avoid that? How can you force the bromine to go where it doesn't necessarily want to go? You can block the para position temporarily. You can put something here, this is what's been shown at the bottom, you can put something in here, a blocking group, a protecting group, and that takes up the para position. Again, if you've blocked the para position, you can't put anything at the para position. It's taken up. So after that, you can do your chemistry. You might have to force this. Maybe you'll have to heat it up a little bit because it's going to an unfavorable place where it's crowded, and that will give you the ortho product. That's fine. But then you don't want this. So you'll have to deprotect. We did this with silicon in the past. We'll probably see it again later with a ether type protecting group. But in this case now, we get rid of that blocking group, and all of a sudden we have a nice, simple, a little bit more work, but a nice, simple path to the molecule that we're after. Hello, Brianna. Well, in this example, because the blocking group it's a good question. The blocking group is going to be a meta-director, right? So the question is, why doesn't it go down here? And the answer will be because the blocking group that we use, sulfonic acid, is a meta-director, and in this problem, that's sort of, yeah, 2 + 2 = 6. They both send to the same place. 2 + 2 does not equal 6, people. Okay. So this is how we do this. We take benzene, and we add on the SO3H group. And that SO3H group comes about from mixing SO3 with H2SO4. Now, I've had this question this week, and it's a good one. You're quite welcome to say fuming H2SO4 in a problem. But it behooves you, I think, to make sure that you realize that it's angry because you've had an SO3 bubble through it. Make sure you recognize SO3 is in there, because that's where the SO3 group comes from. That's what makes it SO3 fuming sulfuric acid. But under those conditions, you can get the sulfonic acid. You can isolate it, and then away you go. But then, under different conditions, you can get rid of it. You can protonate the benzene ring, and you can lose the SO3H group and go back to benzene. That mechanism is just the opposite of what we did. Protonate, lose SO3, rather than pick up SO3, lose H. It's exactly the opposite. So now we have a concept where, very much like the TMS group for the alcohols when we did Grignard chemistry, we've got a problem where we want to put a group at the ortho position, but the ortho position is blocked, so let's block the para position. Let's use our slightly annoyed sulfuric acid mixture and put an SO3H group at the para position temporarily, because now it's blocked, and, to answer Brianna's question, this is also a meta-director. We want our bromine to go here. So now we have two groups sending it there. You've got the SO3H group meta-directing and the T-butyl group ortho-directing. They both are sending it to the same place, and that will give you this species. And then we get rid of that by adding dilute sulfuric acid, and we have the product we want. So these are the types of games we play. You have to be creative, you have to be careful, you have to be clever in terms of how to do these things. And as we head towards that 34-step synthesis that's in one of the problem sets next semester, yes, we needed to do these things. You'll need to put it all together. It can be fun or a nightmare, depending upon how much time you put in. So with that in mind, there is a slide I think I'll finish on. This is the summary, I think, of where we've just been for that chapter so far. And we can see now some fairly simple methods for putting on bromine. In this example, I use AlBr3 or FeBr3. It's the Lewis acid component that's key. Want to make a chlorination happen? Put in some chlorine with some AlCl3. Want a nitrate? Now in recitation we've been pushing this. We've been saying you don't learn the mechanism 5 times. You learn the electrophile. You learn what is the E+ that I need to make, because the mechanism after that is identical for each of the 5 instances. So in this case, nitric acid, I'm making an NO2+. Know how to do it. In this example, I've got SO3. Know it's in there. Go attack it. That's your E+. Away we go. Here, there's a little bit of confusion here. There's an argument here about do you get a carbocation or not? And that comes down to fundamental stuff from SN1, SN2 last year. Primary systems, no carbocation. Secondary, yeah, okay. Tertiary, sure, no problem. Problem with carbocations is they rearrange. But if you can get an alkyl group on there, you can do other things with it. What is that position right there? Benzylic. And that benzylic position is enhanced in its reactivity. You put a radical there, it's stabilized. You put a carbocation there, it's stabilized. So you can do SN1 reactions. You can do halogenations. If you want to brominate, for example, with Br2 and heat or MBS, you can put Br groups on there. That's how you could make that CBr3 group. Just do it again and again and again. Some little side reactions. If you were to try and take the nitro group out, we saw this. You can make an NH2. So I would say that this slide is useful as a summary for what you need to know from that chapter so far. I will ask you to do some of these things, especially on that page that gives you 20 points worth of problems where it says give us the products. You know, these little details here add up. Know what the tin does, know what the zinc does, know what the Fe does to be able to reduce these things down. And then when we get back after the break, we will talk about synthesis in great detail. So again, I need to be home by 3, but tomorrow I'm pretty much open. If you've got questions by email, send them like that.